Welcome to a video on thermodynamics, spontaneity, entropy, and free energy. Previously this semester we've studied kinetics, which is the study of reaction rates, answering the question, how fast does the reaction go? Then we moved to equilibrium, which is the study of reaction position. Where will the reaction go? Where will it come to rest? Now notice, neither one of those two ask the essential question, which is, will the reaction go? And that's what our study of thermodynamics hopes to ask and answer. When we talk about a reaction occurring, we will often use the word spontaneous. When we use the term spontaneous, what we're saying is that the reaction or the process will occur on its own, without sustained external force. So for instance, when we mix an acid and a base, that reaction occurs. We don't have to sit and stir it, we don't have to heat it, it simply occurs on its own. We argue that that reaction is spontaneous. Now, back in the first term, our initial study of thermodynamics concerned itself entirely with thermochemistry, simply the transfer of heat from reactants to products or products to reactants. The first law of thermodynamics, I hope you recall, is that the energy of an isolated universe is constant, or the change in energy of the universe is zero. Again, this language, delta X, is the change in X. For us, with chemical reactions, delta X of reaction is going to be whatever X is of the products minus reactants. And delta X in our chemical language is always going to be products minus reactants. We also saw that the energy change of the system is going to be the heat that the system gains, or the heat put into the system, and the work done on the system. Remember, when delta E is positive, it has gained heat and or gained work. We found that work wasn't really the best variable for us when we're talking about chemical reactions, and so we moved to what we call enthalpy. And the enthalpy change for the reaction is simply the heat that is transferred at constant pressure. And then we looked at this equation based on Hess's law, which simply says that the entropy change for enthalpy change for a reaction is going to be the sum of the enthalpy of formation of our products minus the sum of the enthalpy of formation of our reactants. And those delta H sub F's, the enthalpies of formation, are how much heat is transferred when we make 1 mole of one substance from its elements in their standard states. You may need to go back and look at your first term notes and refresh your memory on that, because we will not be spending a lot of time on enthalpy. I'm assuming that you remember that. Note that the enthalpy change of the reaction only tells us how much heat is emitted exothermic or absorbed endothermic by the reaction. It doesn't actually speak, again, to the essential question, will this reaction occur? Our present study will seek to tie this thermicity of the reaction, the enthalpy, and nature's tendency toward randomness or chaos, which we'll call entropy, to determine the spontaneity of a reaction. Here are 3 examples of spontaneous reactions at 25 degrees Celsius. Ice melting, solid water going to liquid water, hydrogen and oxygen gases reacting to form liquid water, and iron and oxygen reacting to form rust, or iron 3 oxide. Notice that all 3 of these are spontaneous at room temperature, but only the latter 2 are exothermic, negative delta H, negative delta H. So thermicity cannot tell us whether the reaction is going to be spontaneous or not, because the first reaction is endothermic, but is still spontaneous at room temperature. Let's also note that the first reaction takes us from a highly ordered system, a solid, to a less ordered system, we have an increase in disorder as we go from solid to liquid. The second and third reactions, however, take us from disorder, gases, to order, a liquid or a single solid. Again, notice we go from two things here to one thing. On this reaction, we go from two things to one thing. So the first one is becoming more disordered. The second and third ones are becoming more ordered. So we find that the change in order of the system is also not a single indicator of reaction spontaneity. I would also point out to you that this first reaction, the melting of ice, is only spontaneous if the surroundings are at 0 degrees Celsius, 273 Kelvin, or higher. So temperature is also going to be a factor and must be considered when we're reckoning reaction spontaneity. Please also note that spontaneous does not imply anything about the speed. My favorite example is that diamonds are spontaneously converting themselves to graphite every day. However, the scale of the reaction time is so long, the rate is so slow, that we'll never observe that happening. So your diamonds are safe. Now, the thermodynamic term for this randomness or disorder is entropy and has the symbol S. Notice that we're using a capital S, so it is indeed a state function. All we need to know is where we start and where we finish. We don't need to know the pathway. And we observe that it is natural for systems to go from order to disorder. If we went into my backyard right now and you saw a pile of bricks and a bag of mortar and a couple of metal grates, and we would go, look, there's all the things to build a barbecue. And we went back in the house. And we went back in the backyard tomorrow and there was a new barbecue grill fully constructed. Would that have happened spontaneously? You know it wouldn't. We have to do work to do that. On the other hand, if I have a new barbecue grill that I built in my backyard and we go out there 15 years from now and it's broken bricks and rusted metal, is that natural? Yes, it is. This is an example then again of nature's tendency to disorder. On a simpler scale, let's look at this. Two gases will always spontaneously mix. If I spray perfume in the back of the classroom, in just a few minutes, you smell it in the front. What happened? That the odor-causing chemicals in the perfume and the gas phase have made their way to the front. They spontaneously mix. Heat flows spontaneously from a hot body to a cold body, equalizing and randomizing the thermal energy. Because we give it more space in which to exist, it takes more space. This again is an example of nature's tendency to randomize or to become disordered. We must then consider the universal nature of entropy. There are three very important names regarding entropy. There are more, but three important ones: Clausius, Boltzmann, and Kelvin. Clausius made this statement: heat can never pass from a colder body to a warmer body without some other change occurring at the same time. Boltzmann says that the universe will always move toward a state with a greater number of ways to distribute its energy, or in other words, it will spread its energy out. That's what nature does. That's a natural thing. Kelvin's statement of the second law says that it's impossible for heat to flow from a hot body to a cold body without doing work. Our modern statement of the second law of thermodynamics ties all of that together into what is a simpler statement. All spontaneous processes are accompanied by an increase in the entropy of the universe. Nothing occurs naturally without the universe becoming more energetically disordered. Nature tends toward disorder. Mathematically, we simply say this, that the change in the entropy of the universe is greater than zero, is positive for all natural or spontaneous processes. Now remember, the universe consists of two parts, the system and the surroundings, and so the entropy change of the universe can also be given as the sum of the entropy change of our system and the entropy change of our surroundings. And again, the second law says that's always going to be greater than zero. So if the system becomes more ordered, so the entropy change of the system is less than zero, then the surroundings must become more disordered. Entropy change of the surroundings is greater than zero, so that the sum of system plus surroundings is greater than zero. That's the second law. Now notice the problem is we still have to look at both system and surroundings. We have to examine the entire universe to discover whether a reaction will occur or not, and that is not what we want. Now, the second law of thermodynamics, again, that the entropy change of the universe is greater than zero for all natural spontaneous processes. Now, we're going to define our entropy change, delta S, as Q over T. That is to say, the heat that is transferred divided by the temperature at which the transfer occurs. Let's consider the following example, a melting ice cube. Let's say that my system is 1 mole of ice frozen. Now this ice is at 0 degrees Celsius, 273 Kelvin, until all melted. The surroundings are at 25, 298 Kelvin. So if 1 mole of ice melts, it absorbs 6,000 joules of heat at 273.15 Kelvin, and the system loses 6,000 joules of heat at 298. So the entropy change for the ice is going to be plus 6,000, it gains 6,000 joules, divided by 273, or plus 21.96 joules per Kelvin. The ice becomes more disordered. Delta S ice is positive. The surroundings loses heat, negative 6,000 joules, at 298.15 Kelvin. So its entropy change is negative 20.12 joules per Kelvin. The surroundings actually becomes more ordered because it loses heat. When we then compute the entropy change of the universe, the entropy change of the ice plus the entropy change of the surroundings, we find that the sum is positive 1.84 joules per Kelvin, which is greater than zero. So we have proven that ice will melt spontaneously at room temperature. Now, this example is worked out to illustrate and not to be reproduced. I'm not going to ask you to do this at this level. So we at this point still have to calculate a universal property just to know if the system reaction is spontaneous. And as I said earlier, that is not going to work. Before we find a solution to our problem, we need to talk briefly about what is called the third law of thermodynamics. Now, the only way for us to have zero entropy or no disorder is to have only a single possible state that the system can be in and to have no energy to exchange. This theoretical state is codified in what we call the third law of thermodynamics, and it simply says this, that the entropy of all pure, perfectly crystalline substances at 0 Kelvin is 0. So if it's pure, there's only one thing, there's no material randomness. My sock drawer is all white socks. Every time I pull out a sock, it's white. It's perfectly crystalline. That means that every molecule in there is oriented exactly the same, and it's a perfect crystal. In my sock drawer, every pair is perfectly joined. I can't pull out one, I can't pull out three, I can only pull out two at a time. And there's no energy. So my sock drawer is always locked, so no one can get in there and mess with it. Now the problem with that, if my sock drawer is always locked, I can't get to my socks. Here's the problem with the third law. I must have a pure substance. Maybe I can get it pure. In reality, I can't. I have to get it perfectly ordered. Maybe I can. In reality, I can't. And it must be at 0 Kelvin. It must have no heat. And if it ever comes in contact with anything, it's the coldest body and it will absorb heat. So even if we can get to absolute zero, we can't stay there. So it has to be pure, theoretically possible, not reality. It has to be perfectly ordered, theoretically possible, not reality. And it must be at 0 Kelvin. My argument is not even theoretically possible, but not really possible either. Now, symbolically, we just say this. This third law entropy, we call it S super zero or S0. For a pure perfect crystal, temperature equals 0 Kelvin is 0. Now, these third law, or what we'll call absolute entropies, define our 0 point. Now, there are two conclusions we can draw from the third law. One, we can't get to absolute 0 Kelvin, and more importantly for us is that all real substances at real temperatures have positive entropies. The entropies are going to be greater than 0. Now, here's 3 properties of entropy that you need to know. For a single substance, a gas is going to have a higher entropy than a liquid, is going to have a higher entropy than the solid. Or speaking in order terms, gas is most disordered, liquid is less disordered, and solid is least disordered. We're also going to find that the entropy increases as the temperature increases. The more heat we give it, the more disordered it can become. And for similar structures and states or phases, we're going to find that the entropy is going to be an increasing function of mass and size. Big things are going to have higher entropy than small things, generally speaking. We now want to turn to reaction entropies. If we're going to discover whether a reaction is going to be spontaneous or not, we're going to need to know its entropy. Now, we calculate reaction enthalpies by using enthalpies of formation. Similarly, we calculate reaction entropies by using third law or absolute entropies. Notice that the equations are the same, products minus reactants. So the form of the equation is what we saw in enthalpy back in chapter 8, and we're using the same state function principles to calculate entropy here. Here's an example. Hydrogen plus oxygen makes water. So the entropy of reaction is going to be the entropy of my products minus the entropy of my reactants. This equation tells me that I'm going to need twice the entropy of water because I've got 2 moles of water minus twice the entropy of hydrogen plus 1 times the entropy of oxygen. Now, taking the values from S0 in a table, from a table in the textbook, and you'll be provided with these numbers when you need them, we find that the molar entropy of hydrogen is 130.7 joules per Kelvin per mole. For oxygen, it's 215, and for water, it's 69.9. Now, let's notice the smaller gas, hydrogen, has a lower entropy than the larger gas, oxygen, and the liquid has a lower entropy than the gases. Again, that's what we talked about earlier. Big things, higher entropy than small things, so oxygen has a higher entropy than hydrogen, and liquids have a lower entropy than gases. If we do the math, we find that this reaction, plugging the numbers in, there's products minus reactants. This reaction has a negative entropy, telling me what? That the products have less entropy than the reactants. In this case, we can argue this 2 ways. One, we've got gases becoming solid, disorder becoming order. And we've got 2 things, hydrogen and oxygen, becoming 1 thing, water. So we're happy with that answer being a negative number. Now, because we now have a method of doing enthalpies and entropies, we turn our attention and we give our thanks to the good work of J. Willard Gibbs. And he has provided us with a single system variable to determine reaction spontaneity. Gibbs defined what he called the free energy function, G, as G is equal to H, enthalpy, minus Ts, temperature and entropy. Now, for a reaction at constant temperature and constant pressure, which are our most common lab conditions, we have that delta G of reaction is equal to delta H minus T delta S. This is a very important result. And it may be proven, I don't do it here. If you need to see it, come and see me outside of class. It may be proven that if the free energy change of reaction is negative, less than 0, the reaction is spontaneous, left to right, as written. That means the reverse reaction has a positive delta G, and it's not spontaneous. G, again, capital G, so it's a state function. If it's negative going left to right, then it's positive going right to left, just like enthalpy. If delta G, the reaction is positive, then the reaction is non-spontaneous left to right, and the reverse reaction is spontaneous. Special case, or third case, if delta G is 0, then the reaction is at equilibrium. So looking at this equation, we know how to calculate delta H for the reaction. We know how to calculate delta S for the reaction. We can now calculate delta G for the reaction, and we can finally ask and answer the question, will this reaction occur? Is it spontaneous? Now, in general, let's look at the following table. Again, notice here, there's my equation for delta G in terms of delta H and delta S. Now, there's two possibilities for H. It's either positive or negative. There's two possibilities for delta S. It will either be positive or negative. So that means there's 4 cases. They're both positive, delta H is positive and delta S is negative, or delta S is negative and delta H is positive, or they are both negative. I want to look at the 2 middle cases first. Let's look at case number 3, where we have a negative delta H, exothermic reaction. It's going energetically downhill, and a positive entropy change. So this is a car that's rolling downhill and falling apart as it goes. Mathematically, that means we're going to have delta G is going to be a negative minus a positive. That is always negative, regardless of what the temperature is. So an exothermic reaction that has a positive entropy change is always spontaneous. The exact opposite, if delta H is positive and delta S is negative, so that I'm taking a positive and subtracting a negative, that answer is going to be positive at all temperatures. And that means that type of reaction, it's endothermic and the entropy change is negative. Such a reaction is never spontaneous. Now hear me, that doesn't mean it never happens. That means it never happens on its own. We could provide enough work or enough energy to force it to happen. Okay. But a car is never going to assemble itself as it rolls uphill. That will never happen. Can a car fall apart spontaneously as it rolls downhill? All day long. So those are my 2 cases where we have always or never. The other 2 cases are when the enthalpy and the entropy are of the same sign. In this case, notice delta H is positive and delta S is positive, so that would be a positive minus a positive to get to delta G, and it would be positive then when T is small, low temperature, and that difference would be negative when the T is high, at high temperature. So when is such a reaction spontaneous? At high temperature. The fourth case is when both are negative. It's an exothermic reaction, but it has a negative entropy change. Notice that's going to be negative when T is small because that's negative minus a negative. It will be positive at high T. That's a small negative minus a big negative is going to be a positive number. So when is it spontaneous? When is delta G less than 0? That's going to be at low temperature. So this is a reaction that's going to be spontaneous at low temperature, and this is going to be a reaction that's spontaneous at high temperature. Let's look at an example. Here's a reaction between silane and fluorine gas to give me silicon tetrafluoride gas and 4 moles of hydrogen fluoride gas. You are given the enthalpies of formation in kilojoules per mole and the third law, or absolute entropies, in joules per Kelvin per mole. Now, I pulled these out of a table. Where would you find them? Either in such a table, if I give you access to that, or on an examination or a practice set, I will give you those values. The problem then says, given this, let's calculate delta H, delta S, delta G at 298 Kelvin, and state whether the reaction is spontaneous at that temperature. And let's recall, delta H is products minus formation for standard enthalpies of formation. The entropy is products minus reactants for absolute entropies, and delta G is delta H minus T delta S. Here's the calculation for the enthalpy change of reaction. It's my products, so 1 times 1614.9 plus 4 times negative 271.1. Those are my products, and I react 1 mole's worth of enthalpy for the silane, 34.3, and 2 times 0. That's an element in its standard state. That math then turns out to be negative 2699.3 minus 34.3, or an enthalpy change of negative 2733.6 kilojoules. This is highly exothermic. The entropy change, again, is going to be products minus reactants. 1 times 282.49 plus 4 times 173.8. There's my products. And I subtract my reactants. 1 times 204.62 plus 2 times 202.8. That turns out to be 977.69 for my products, minus 610.22 for my reactants. So we have a positive entropy change of 367.47 joules per Kelvin. Notice, this is a reaction that gives off heat, so it's going downhill energetically, and it becomes more disordered. We go from 3 moles of gas to the left to 5 moles of gas on the right. So it has a negative delta H and a positive delta G. And that's going to be a case where this reaction then is always spontaneous. Let's also note that delta H is in kilojoules and delta S is in joules per Kelvin. So to calculate delta G, we must convert delta S to kilojoule units. So I've divided this number by 1,000 to go from joules to kilojoules. Delta G then can be calculated as delta H minus T delta S. We do the math. We're told we're at 298 Kelvin, and delta G turns out to be negative 2843.1 kilojoules. And because delta G is negative, the reaction is spontaneous at this temperature. And again, because this reaction is exothermic and has a positive entropy change, so that's negative and that's positive, this reaction is always spontaneous. Let's look at another example. Here is silicon dioxide, quartz, plus 4 moles of hydrofluoric acid becoming silicon tetrafluoride gas and 2 moles of liquid water. We wanted to calculate the same three thermodynamic functions, delta H, delta S, and delta G, and we want to state whether the reaction is spontaneous at that temperature. We want to ask one more question, however, and ask at what temperatures is this reaction spontaneous? The one we just looked at was spontaneous at all temperatures. We're going to find this one is not. Here again, I'll let you follow the math, but delta H is products minus reactants. I'm pulling the numbers from up here, products, reactants. This turns out to be exothermic. This is exothermic. The value is negative 191.7 kilojoules. Here's the entropy change. Again, products minus reactants. Products minus reactants. When we do that, it turns out to be a negative entropy change. Negative 314.7 joules per Kelvin. Notice that is a reasonable answer because we're going from a solid and 4 moles of gas to a gas and 2 moles of liquid. So this should be more ordered than that. So reactants minus products, small entropy minus large entropy should give us a negative value, and it does. Again, I've divided by 1,000 to get that in kilojoules per Kelvin, and delta G is delta H minus T delta S. So here we go. I forgot to move that number down. That's all right. This is negative 191.7 minus T delta S, which is a negative 93.7. Delta G is then negative 97.9. That's less than 0, and so it is spontaneous at this temperature. Now, because this reaction is exothermic but has a negative entropy change, it is spontaneous at low temperatures. So in this case, 25 is a low temperature, 298 is a low temperature. Now, that means at some temperature, in this case, at some temperature G, delta G is going to be 0, and that means that delta H minus T delta S is 0, and that delta H must equal T delta S. At this temperature, the reaction is at equilibrium. This reaction will be spontaneous below that temperature. So at that temperature, delta H is equal to T delta S, or solving for T, T is delta H over delta S, dividing 191.7 kilojoules by negative 0.3147 kilojoules per Kelvin gives me a temperature of 609.1 Kelvin. So this reaction is spontaneous at temperatures below 609.1 Kelvin. If we plug in a temperature higher than that, if we plug in 700 Kelvin, we'll find that the delta G we calculate is positive. That means it's not spontaneous at 700. When did it change spontaneity? When it went from a negative delta G to a positive delta G, and that means it passed through 0. So the 0 T, the temperature at which delta G is 0, is the transition temperature, transitioning from spontaneous to non-spontaneous. The last thing we want to talk about with thermodynamics is the relationship between free energy and the equilibrium constant. It may be shown that the free energy change is equal to negative RT times the natural logarithm of KEQ, or solving that for KEQ, KEQ is equal to E to the negative delta G over RT power. This R is just a thermodynamic constant that we saw in the ideal gas law, that we saw in the osmotic pressure formula. We also see it here in the relationship between delta G and equilibrium constant. It is a thermodynamic constant. The units that we want here are joules, And so R is going to be 8.3144 joules per Kelvin per mole. You will always have access to that value. On an exam, I'll put it on the formula sheet or include it in the problem statement. Don't memorize that number. We don't memorize numbers in my class unless we have to, and we don't have to memorize that one. Now, let's notice mathematically then, if delta G is negative, that means that's e to a negative negative or e to a positive value, then K is greater than 1 and the products are favored. If delta G is positive, then the equilibrium constant is less than 1 and reactants are favored. And if delta G is equal to 0, then the equilibrium constant is 1 and we would expect to get roughly equivalent amounts of products and reactants. Let's pull the delta G value from the example on the previous slide. There, delta G was negative 97.9 kilojoules or negative 97,900 joules. That means we can calculate KEQ as negative delta G over RT. So we're doing this at 298. That's e to the plus 39.513 power, or an equilibrium constant of 1.45 times 10 to the 17th power. That's a very, very large equilibrium constant. We're going to get virtually all products. So when delta G is negative, we get an equilibrium constant greater than 1. When delta G is a large negative number, we get a very large equilibrium constant, and we would argue that the reaction goes to completion. When delta G is positive, the reaction is not spontaneous. When delta G is positive, we get an equilibrium constant that's less than 1. When delta G is a large positive number, you will find that the equilibrium constant is a tiny number, 10 to the negative a lot. And what do we say when we have a very small equilibrium constant? We essentially have no reaction, very little product. It's almost all reactants. This concludes our second excursion into thermodynamics with entropy, spontaneity, and free energy.